Bismillahirrahmanirrahim. Dear student, in our previous lessons, we learned that the elements combine together in order to attain the noble gas configuration. They make a chemical bond. It might be a covalent bond, ionic bond, and in case of pure metals, we discussed about the metallic bond as well. Today, we are discussing that when these elements combine together, whether they attain a specific geometry or not. This is what related to our today's lesson. And let the elements, when they are going to make a bond with each other, there will be two sorts of electrons. One will be the bonded electrons, and the second would be the unshared electrons, or the lone pair of electrons. This is what we are going to discuss in our today's lesson. Dear students, a chemical formula reveals a little information about the molecule's geometry. After performing many tests designed to reveal the shapes of the various molecules, chemists developed two different equally successful theories to explain certain aspects of their findings. One theory accounts for the molecular bond angles. The other is used to describe the orbitals that contain the valence electron of the molecule's atom. Let if an element is going to make a bond with another element. For example, this is hydrogen and this one is chlorine. When they're sharing its 1 electrons, we will get a geometry for this molecule that is a linear structure because there's only one hydrogen and one chlorine over here. They share their 1 electron. So in order to understand the more complex molecules, which contains more than two elements that combine together, in that case, we have to focus on the number of electrons in the valence shell of these bonded atoms. These electrons might be the bonded electrons and lone pair of electrons. So in order to understand this one, we will go through a theory, and it is known as the valence shell electron pail repulsion theory, this one. In simple, we can say VSEPR theory. The VSEPR theory states that repulsion between the sets of valence level electrons surrounding an atom causes these sets to be oriented as far apart as possible in order to achieve stability. If we are going to take the examples of BeF2, beryllium fluoride. Now this beryllium fluoride atoms forms a covalent bond with each fluorine. If you look over here, you can see that each beryllium is going to make a bond with two fluorine, a covalent bond. Although it's not going to obey the octet rule, this is the exceptional case we learned already. So it is surrounded by only two electron pairs it shares with the fluorine. So if you focus the beryllium at the center, you can see that there is only two bonded electrons on each side. There isn't any lone pair of electron here in beryllium. So dear student, according to the VSEPR theory, if there are two elements that are attached to the central one, that is beryllium in this case, and there isn't any sort of lone pair of electrons, they will be apart maximum from each other. So over here, they will give us a linear structures and a bond angle of 180 degrees. They will be completely in opposite direction of each other. So the structure of beryllium fluoride is linear in structure. Now we will discuss all this in a general representation. Dear student, look into this one. If we are representing the central one, that is the beryllium, as a letter A, and the rest of the element that are attached with the central element as B. So for BeF2, the general representation will be AB2. A means the central element, B means the other element attached with the central one, and if it is 2 mentioned next to B, it means that 2 elements are attached to the central one now. So if we have this configuration AB2 molecules, understand that the bond angle over will be 180 degree, and the structure will be linear in structure. And if we have molecule that we call it AB3, in this case, it is mentioned over here, AB3. So it means that we have one central element and three bonded elements. Still, we didn't discuss the lone pair of electron in the central because that topic we will discuss in the next examples. So A means the central element, and B3 means three elements are attached with the central element. If we have any molecule that's going to follow this one, AB3, over there the geometry will be, the bond angles will be a 120-degree, the angles, and uh, the corners, we can say that it looks like a triangle, or simply in geometrical term, we can say that it's a trigonal planar geometry. We can say it is a trigonal planar geometry. And the example of this sort of molecules are BF3, where B is the central element followed by 3-fluorine. So if we are talking about AB4, I will just show you this structure in the PhET simulation as well. A is the central element, and the 4 means 4 rest of the elements are attached with this central element and gives us a geometrical structure having a bond angle of 109.5 degree. And this sort of structures are known as tetrahedral structure. We can say that these are the tetrahedral structure. So again repeating, BEF2, the three elements lie in the same plane having the linear structure. BF3, the central element attached by the 3-1, we can say that it is a trigonal planar geometry. The bond angle will be 120. They are maximum far apart from each other. And in case of AB4, it has a tetrahedral structure having a bond angle of 109.5 degree. Dear student, in this simulation, we will go through all the types of structure that we learned right now. If we have only two elements like hydrogen and chlorine, hydrochloric acid, so the over here, the structure will be linear in structure. And if we have three elements, and there isn't any lone pair of electron, this lone pair of electron we will discuss in our next examples. So there is only bonded electrons, not lone pair of electron. At that time, the bond angle would be 180 degree. You can see it's 180 degree, and the structure molecular geometry would be a linear. Over here, you can say that it is a linear structure. It is here in front of you. But if we have AB3, means A is the central one, and then attached by the three elements, you can see that it has a bond angle of this one, 120. So, and the structure will be trigonal planar. They are maximum far apart from each other in order to reduce the repulsion. This structure is more stable structure for the molecules. They are following AB3 rules, like BF3 molecule. Regarding the tetrahedral now, dear student, look, in tetrahedral, the bond angle is 109.5 degree. This is the central atom attached by the four other elements. The example is CH4 methane. Carbon is the central one attached by the 4 hydrogen. So at each possible angle, you can see that degree, you can see that the bond angle will be at 109.5 degree. If I'm going to decrease it, and if I will leave the bonds again, it will go maximum far apart from each other. And the ideal position for this sort of molecule exists at a bond angle of 109.5 degree. And we call this sort of structure as tetrahedral structure. In our next lesson, we will discuss the effect of unshared electrons, or we can say the lone pair of electrons, on the geometry of a molecule. This was all about today's lesson. Thank you very much.